All right, the last section in chapter 13, we're going to talk about colligative properties. And remember, colligative properties from last year, we've talked about colligative properties and the different types of colligative properties and how colligative properties work. So this is mostly going to be review, but let's go ahead and review it. What are colligative properties? They are properties that change in solution depending on the number of particles of solute that is dissolved. So they are really dependent upon the number of particles of solute present, or the concentration, or how much is dissolved in the solution. The four major colligative properties are vapor pressure, boiling point elevation, melting point depression, or what last year we called freezing point, and osmotic pressure. So those are the four colligative properties. Vapor pressure. All right. Vapor pressure is affected by the concentration of solution. Why? Well, due to the intermolecular attractions in molecules, all right, it makes it harder for solvents to escape in the vapor phase due to those intermolecular attractions. Therefore, vapor pressure of a solution is lower than that of a pure solvent. If we want to solve for vapor pressure of a solution, all right, PA is equal to XA times P degrees A. XA is the mole fraction of the compound, which we've learned how to solve for in the last section, 13.2, and P degrees A is the normal vapor pressure of A at that temperature. So that would help you solve for the vapor pressure of that solution. Boiling point elevation and freezing point depression. Remember, anytime you add something to a solution, it most likely raises the boiling point and lowers the freezing point. And we've talked about this with salt, how salt does that role. It raises the boiling point of water and it lowers the freezing point of water, and it also is dependent on concentration. Now we have talked about this last year, so I'm not going to spend a whole lot of time going over this. This will be mostly review, but remember, the change in boiling point is equal to change in TB, or the change in the boiling point temperature, is equal to KB times M. KB is the boiling point elevation constant, which is different for every single solution. Last year we dealt mostly with water, and if you look on that graph, it's kind of difficult to see. I should probably blow this up here a little bit, but you can see that the boiling point elevation, or KB, of water is 0.51. M is the molality of the solution. So anytime you have boiling point elevation, change in TB, it's equal to KB times M. We did those problems last year, telling you how much it's going to raise. Now, if we do the same for freezing point, equation is the exact same for freezing point, except for the fact that instead of using KB, the boiling point constant, you're going to use Kf, which is the freezing point constant. Kf is different for each substance as well. For water, it's 1.86. And so you can see what it is on the graph based on a variety of things. So Tf is equal to Kf times M, Kf again being the freezing point, M being the molality. So remember, those are the two equations. We've practiced with those two equations. Nothing new is going to come from those two equations. Now, when we talk about colligative properties of electrolytes, remember, an electrolyte is a solution that's conducting electricity that helps, a solution that's dissolved in water that can conduct electricity. So something to keep. So when we talk about electrolytes, remember something like salt. When salt dissolves in solution, it breaks up into ions, and if you have 1 mole of salt, it's going to break up into 2 moles of ions, 1 mole of Na and 1 mole of Cl, and you would think that that would affect the colligative property, right? So here we have an example. It says this exactly on the slide. However, when 1 mole solution of NaCl does not show twice the change in freezing point of that of methanol. Remember, methanol is not going to dissociate. So why is it that NaCl has 2 moles of ions, but it doesn't show twice as much? And it has to do with what we call kind of the Van Hoff factor, which 1 mole is not going to give really fully 2 moles of ions. And that's because some of them are going to reassociate for a short period of time, which means that the concentration is going to be greater than 1, but not exactly 2. So some of those NaCl ions are going to reassociate for a small amount of time, keeping the concentration under 2. Now, reassociation is more likely to happen the higher concentration of solution you have, so therefore this is a colligative property and it's concentration dependent. So if we modify the equation filling in the Van Hoff factor, we're going to add our I to the equation. We're not going to focus too much on the I just want to give rise to, on a free response question, you might have to explain why NaCl doesn't give twice the value of methanol, and the Van Hoff factor is the exact reason why. Some of those ions reassociate. So just a little explanation there. Last of the 4 colligative properties is osmosis. Remember, osmosis is when solutions or particles transfer through a semi-permeable membrane. So they allow small particles to pass through, but blocking larger ones. So imagine that you're sitting on the baseball field on the outfield fence. You can pass golf balls through the chain link fence, but you can't pass baseballs through that fence. So the golf balls go through just fine, and the baseballs get stuck. So something to kind of keep in mind. This is a biochem thing all the way. It's in biological systems. Semi-permeable membranes exist throughout the cells and throughout the body. A couple things about osmosis. They always go from a higher concentration to a lower concentration, something to keep in mind. And then you always want to solve for osmotic pressure. And how do you solve for osmotic pressure? Well, osmotic pressure is pi, and that is equal to N over V times RT, or the molarity of the solution times RT. So N is moles, V is volume, R is our R value, and T is temperature. So MRT is the molarity, and then R and T are our values that we've used for, and you're solving for pi, which is osmotic pressure. Osmosis happens in blood cells all the time. Like I said, this is kind of more of a biochem thing. I'm just showing a couple examples of where osmosis can happen. It happens in blood cells. It happens in regular cells. And it exists all over the place. So that is kind of all we have. Don't worry about the Tyndall effect or colloids. We're going to talk about those a little later when we talk about a little bit more about solutions and suspensions and precipitates in the next chapter when we talk about solutions. So that kind of concludes section 13.3. Remember, we have colligative properties. The 4 colligative properties: vapor pressure, boiling point elevation, freezing point depression, and then lastly, the one we just got done talking about, which is slipping my mind for some reason, the last one, number 4, osmosis. So those are the 4 colligative properties, and they're all affected by the concentration of a solution, and this concludes 13.3.